Okay, exercise number 4. We take a closer look at all the isomorphisms going from one group to itself. And such an isomorphism is called an automorphism of the group G, and the set of all these isomorphisms is called out G. The automorphism group, or aut G in English, the automorphism group of the group itself. So this here does not consist of group elements, but of bijective maps that are homomorphisms from G onto G. And in part A, we should convince ourselves that this is actually a group operation, of course, being composition of maps. So we know since problem set 1 that composition of maps is always associative. So that's a nice thing. We do not have to check this again. We clearly have an identity, which is simply the identical map, it sub G, going from G to G, doing nothing. This is clearly bijective, this is clearly a homomorphism, so it is an automorphism, and clearly it does not change an automorphism when composed with it. And the same the other way around, so this shows that this here is the neutral element of this set here together with composition. Now, by definition, for G3 we have to find an inverse to each element, but by definition these here are bijective maps, so they have inverses going from G to G again, and we proved in this lessons video that automatically then phi inverse also is a homomorphism, so actually an isomorphism, meaning that phi inverse again is an element of this set here. It would not be complete to simply say, well, the inverse exists. You need to convince yourself that, again, the inverse also is an element of this set. So again, so the inverse must be an isomorphism, which it is. But you have to show that. Okay, and this taken together shows that this indeed is a group. Of course, most times it will be non-commutative. Of course, this depends on the group G itself. If G is the trivial group, then trivially, the automorphism group only consists of the identity. What other map would there be from the trivial group to itself? But we will see in exercise 6 that the automorphism group of the Klein 4 group is actually isomorphic to S sub 3, the symmetry group on 3 elements, which is not commutative. So even in small examples, this will turn out to be a non-commutative group. Okay, in part B, we look at the so-called conjugation with any group element in G, which sends X to this here, G dot X dot G inverse. We will later see that this is a very important operation on any group, and we need to show that this is always an automorphism. So first of all, is it homomorphic? Well, we take 2 elements of G and take a look at phi applied, not phi, of course, sorry, kappa sub G applied to xy. This is by definition this here, and now the same old trick, we add an identity here, which is always allowed, and we need never worry about parentheses because of associativity. And this shows that this here is nothing but, come on, and this here is nothing but kappa sub G of x times kappa sub G of y, this showing that kappa sub G is homomorphic. But this is not enough. We also need to show that it is an isomorphism, so that it has an inverse map. Now my claim is the inverse of kappa sub G is simply kappa of a sub G inverse y. Let's take a look at this composition here. So first I apply this map here to x, giving me this by definition of conjugation. I multiply from the left with G inverse and from the right with the inverse of G, and then I have to apply this map, which means G and then G inverse. But now G inverse is nothing but G itself. So here the G's cancel and give me the identity, and here the G's cancel. So I end up with X itself, which is the identity applied to X. And since this is clearly true for all elements of G, this shows that this map here, this composition, is nothing but the identity. And of course, the same the other way around. And this proves that this indeed is the inverse map of kappa sub G. And this taken together shows that kappa sub G is an automorphism of G. So in any group, we know all these automorphisms. Okay, in part C, we take all the conjugations by all the group elements together as a set, and then these here are called the inner automorphisms of G, denoted by in G. And now we're supposed to show that this is a subgroup of the automorphism group. Okay, let's abbreviate this with I. Clearly I is not the empty set because there is at least conjugation with the identity. Every group has an identity element. So, and then to apply the condensed subgroup criterion, we need to show that for any two elements here, this composition of this with the inverse of this one is again an inner automorphism. First of all, when proving anything for a map like this, we apply it to an arbitrary group element and take a look at the result. Now, first of all, we show that this here is conjugation with the inverse of H, and now we need to apply this here. So this is kappa G applied to H inverse X H inverse inverse. This is the definition of kappa sub H inverse. Now this is simply H, and this here is the definition of kappa sub G. And again, no parentheses needed because of associativity. And now we need to see that this again is conjugation with one element, and for this we write this here like that. We reverse the order and then take the inverse. Remember, the inverse of AB is the inverse of B composed with the inverse of A. In a non-commutative group, this is important that you change the order here. And now you see this is simply conjugation with GH inverse of X. And so, because this is true for arbitrary elements X in G, we can infer that this composition indeed is conjugation with GH inverse. So this composition again is an element of this inner automorphism set, and by the condensed subgroup criterion we now know that this is indeed a subgroup of the whole automorphism group. So, and finally we need to show that the inner automorphism group is trivial, meaning it consists only of the identity, which is nothing but conjugation with the identity element of G, if and only if the group itself is abelian. So maybe we do it in both, maybe we do it separately with two implications. So first of all, we assume that this is true, and then we need to show that G is abelian. But if this is true, then for any group element, conjugating with it is the identity, because this is the only element of the inner automorphisms. This means exactly that kappa sub G is the identity of G, means that no X gets moved when I apply kappa of G. But that means that for all X we have this here, because this is kappa sub G of X, and this clearly means that G is abelian. Or you could multiply this from the right by G, then you end up with this, And this holds for arbitrary g and x, so we know that g is abelian. And the other direction is similar. Maybe I should have written it down in one try. No, whatever. So if g is abelian, then for any g element g, I'm not going to write that down here again, we have kappa sub g of x is this, and now we can switch the elements, move them around. So I switch those two, and then we end up with x. And this clearly is true for all x in g. That means kappa sub g leaves every x alone, does not move it at all, so kappa sub g is the identity, and this clearly is true for any g in g, showing that the inner automorphism group is trivial. Okay, exercise number 5 on problem set 14. This, I think, is one of the first real problems, because until now mostly we had to use the definitions and just spell them out and do some little things, but do not feel bad if that was hard, because it really is in the beginning. But here you really need an idea. You cannot just say, well, this is this and that, and now I do this and that and end up with this isomorphism, but you really need an idea. And this is what math really is about. So here we need to show that the general linear group of 2 by 2 matrices over the field F2, so the field with 2 elements, 0 bar and 1 bar, so just the residue classes Z mod 2 in Z mod 2, which form a field, that this general linear group here is isomorphic to the symmetric group of degree 3, so or on 3 elements. Well, what do we have here? First of all, I call this group here G. G consists of 2 by 2 matrices with entries in F2. Naturally, they act on such vectors here. In the vector space F2 to the 2, so consisting of all the vectors with 2 entries that can either be 0 bar or 1 bar. Now, every matrix leaves the 0 vector alone, or maps it to itself, because matrix, a linear transformation applied to the 0 vector, is the 0 vector again. So we can exclude this, and then we are left with 3 different elements that I call V sub 1, V sub 2, and V sub 3. So 3 elements, and maybe a matrix in here can permute them. Indeed, that is what happens. So to a matrix here, sorry, this is not written down very well. Oh no, here it is. So we take a matrix in this general linear group, and we associate to it a map pi sub A that goes from this set of 3 elements to itself by simply mapping one of those vectors to its image when A is applied, the matrix. And this here indeed is a bijective map from M to M, because the kernel of every such matrix in here is trivial. It is a bijective matrix, so a bijective linear transformation. So the 0 vector gets mapped to itself, and only the 0 vector gets mapped to itself. So all the other vectors cannot get mapped to the 0 vector, so all these images indeed lie again here in this set. So to every matrix here I can associate a permutation on this set of 3 elements. And this is the core idea of this proof here, or of this isomorphism. So let's take a look at an example. If A is this matrix here, it is clearly an element of the general linear group, because the determinant is 1 times 1 bar, which is 1 bar. And now we apply this matrix to the 3 elements of our set M. Then by matrix vector multiplication, I end up with this vector. 1 bar times 1 bar plus 1 bar times 0 bar gives me 1 bar. And the same in the second row here. 1 bar times 0 bar is 0 plus 0 bar times 1 bar again is 0. So I end up with V1 itself. the terminology of linear algebra would say that V1 is an eigenvector of the matrix. And then you can check that for yourself. A permutes V2 and V3. Simply do the matrix vector product again, and you will end up here with V3 and here with V2. So, what does that mean? We can associate to this matrix here the following permutation. V1 goes to V1, V2 goes to V3, and V3 goes to V2. Now this here is an element of the symmetric group on M, which we write sim M, but of course we can identify this here with this permutation. If we simply relabel the elements, this is 1, this is 2, this is 3, then we end up with this permutation, which in cycle notation is simply the transposition 2, 3. This clearly is an element of S3, and from now on we simply do this identification without further talking about it. Because otherwise I must write here sim M, but it is the same as S3. Well, actually, this here is an isomorphism of sim M to S3 simply by relabeling the elements. There is not much to check. It's clearly bijective and clearly a homomorphism. Now, this here induces a homomorphism, which I call pi, from G to S3 in the following way. A gets mapped to pi sub A plus this identification, that I identify this permutation with this here, so that I end up in S3. And now we need to check that this here is indeed a homomorphism and that it is bijective. So let's do exactly that. So we need to show that pi applied to A dot B, this is the matrix product, is the same as pi of A composed with pi of B, or in this notation pi sub A composed with pi sub B. So those are maps, bijective maps from M to M. So to check that both sides are equal, we simply apply them to all the elements of M, so to all the vectors V1, V2 and V3. Okay, now by definition, this here is pi sub A dot B applied to Vi. Again, by definition, pi does nothing but apply this matrix to this vector. Now, what does this mean? By definition of the matrix product, this means first compute this here, B applied to Vi, this gives me another vector, one of those here, and then apply A to this result here. Yeah, this is the matrix product, but this here is A applied to pi sub B of Vi by definition, and this simply is pi sub A applied to pi sub B of Vi. Again, by definition of this map here. And this is true for all Vi. I runs from 1 to 3. And this shows exactly what I wanted to show, because here we have the composition applied to Vi, and here we have what we started with. So this shows that this map is the same as this, which I should have written like that in the end, but I ran out of space, sorry. So you have to imagine that this here is exactly the composition applied to Vi. So this shows that pi is a homomorphism. Now, is it bijective? Well, yes, because first of all we take a look at its kernel. By definition, the kernel consists of all matrices in G that get mapped to the identity in our set sim M, or since we identified the identity of S sub 3, again we consider this to be the same. So this means that pi sub A applied to any vector changes nothing. So we have this here for all I from 1 to 3. But this means by definition of pi sub A applied to the vector Vi is the same as Vi. But the only matrix that fulfills this is clearly the identity matrix, because 0 never gets moved by any matrix, and it leaves all the other elements of my vector space invariant. So it must be the identity matrix here, or abbreviated capital I. So the kernel of pi is trivial, and because we just showed that pi is a homomorphism, this means that it is injective. That was this one lemma we proved for a homomorphism. Triviality of the kernel and injectivity is the same. But pi is a map from G, which has 6 elements. We did this some problem sets ago, that there are exactly 6 matrices with non-vanishing determinant in all the 2 by 2 matrices over F2. But this is the order of S3. So we have an injective map from a group with 6 elements to a group with again 6 elements. So automatically it must be surjective. So this shows that pi is a bijection, which is also homomorphism. So we actually proved that these groups here are indeed isomorphic. I think this problem deserves the skull, because first of all you need some background knowledge in linear algebra, and again you need an idea how to construct this homomorphism or isomorphism in the first place. Okay, and the last exercise of this nice problem set. We need to show that the automorphism group of the Klein 4 group is also isomorphic to S3. Now, with the result from exercise 5 in the back of our minds, this is not too hard if again you have a bit of knowledge about linear algebra. If not, it is basically the same as here. Simply write the elements of the Klein 4 group like that. This here we write as 0, this here as V1, V2, V3. So we end up with exactly the same set, only in a bit different notation. We do not write it as column vectors, but as these tuples here, being elements of the Klein 4 group. But then the idea is exactly the same. An automorphism always maps 0 to 0. So again, it is determined by the images of these 3, because trivially 0 gets mapped to 0. So again, every automorphism induces a permutation on this set here of the 3 non-trivial elements of the Klein 4 group. And then basically, in the same way as we did here, you can show that this is an isomorphism. I'll skip the details here for this kind of proof, because it is essentially the same as we just did in exercise 5. There is another way. All right, so we consider this here as an abelian group, the Klein 4 group. But Z2 is nothing but F2, the field with 2 elements. So this here is actually the same as this vector space, F2 to the power of 2. Here I write the elements as tuples, here I write them as column vectors, but they are isomorphic as groups. And this here naturally has the structure of a F2 vector space by simply defining a scalar multiple of such a vector to be this here. And there are only 2 cases. Either this here is 0, so we end up with a 0 vector, or this is 1 and we end up with the vector itself. So trivially, the axioms for a vector space or for scalar multiplication are fulfilled. And this is the important part. An automorphism of this here as a group is automatically an element of the general linear group of this vector space, meaning a bijective linear transformation. Why? Because, so by definition, it is a homomorphism from this group to itself, so it fulfills this here. Okay, sorry, I'm starting to run out of space and recording time, so this is a bit messy. I apologize. So this here is fulfilled by definition of being a homomorphism, and to be a linear transformation of this vector space to itself, it must fulfill this here for all the scalars. But again, there are only 2 scalars. So here we have 0, if lambda bar is 0, here we have the 0 vector, and here again, because this is fulfilled, we end up with the 0 vector on both sides. And if lambda bar is 1 bar, here we have phi of v, and here again phi of v, because 1 bar times v is simply v. So trivially, every automorphism of this group is also a bijective linear map from this vector space to itself. This is the key. So simply by identifying this here with basically itself, we see that this group is isomorphic to the group of bijective linear transformations of this F2 vector space. And now, by choosing any basis we like, this always is isomorphic to this group here. We simply choose a basis, and this then gets mapped to the corresponding matrix. And by exercise 5, we already know that this general linear group here is isomorphic to S sub 3. All right, 1 minute left, so maybe to sum it up, there's the brute force solution, which is essentially the same as in exercise 5. We skip the details. This is the elegant solution, but again, you need some background knowledge in linear algebra. That this here, this group is automatically a vector space over F2 by this definition, and then that every automorphism, so bijective group homomorphism, is trivially a bijective linear map from this vector space to itself, because this here is trivially fulfilled for every map from V to V, because we only have two scalars, and then we simply use this result from linear algebra and exercise 5. All right, and here again, we have deserved to write this end of proof box. All right, that's it for problem set number 14. Hope you enjoyed that and that the solutions were helpful to you, and hope to see you soon again. Bye-bye.